This is a conversation looking at different kinds of INL and DNL plots. And some of the things that we find and some of the ways we talk about the different characteristics between some of the INL and DNL plots. And so this turns out to be kind of important whether or not you're building an ADC or a DAC to kind of know how to talk about your design and what your trade-offs are. Or if you're using an ADC or DAC and you go, okay, well, what can I expect when I see certain kinds of specifications? What are things that could happen here? Okay. And remember what you're going to see in almost all these cases. You're either going to have, say, an ADC where you have values on the low end and digital code on the output on the y-axis, inputs on the x-axis. This will be for an ADC, analog input, digital output. Or I'll have a DAC, which will be digital input, and you'll see that on the x-axis, and analog output on the y. And you'll see this again for a DAC, where you have the input digital structure and the analog output on the other side. And you think, okay, that's great. And so what I would expect is a very nice ideal characteristic. And in fact, in all these cases, you see these nice dotted lines. I will say that I really appreciate all of these figures. These did come out. All these drawings were not my own drawings. These are drawings from Phil Allen from his original notes when we co-taught a number of courses together 20 years ago. Just so well done. I'm just going to use them, and I'm just so appreciative of the work he did, and his work and his legacy should continue to live on. So I will just talk about it this way. What you end up finding is that you'd like to have these ideal curves, which is the dotted lines, and that's what you should expect, right? You would see these dotted lines of what you would like to see. You just expect constant stair step, and you expect a stair step increase of 1 LSB every single time, right? There's a full scale range, and so it's like some percentage of the full scale range. All right, so now the question is what happens? And there's things you would like to have. Now, one such characteristic is that everything might be just shifted up by a certain amount. And that would be what you would typically just call an offset error. And that's actually pretty easy to account for. There's also things which are gain errors, which is a little more annoying because you might actually lose a couple codes at one edge or the other. But again, it just turns out to be a multiplicative factor at the back end. And that we will see in these measures of INL, which is integral nonlinearity, which you're not really doing integral of, you're just taking the difference between ideal and actual. And differential nonlinearity, which is the difference between the difference between actual and ideal at each step. So it's a little bit more of a fine sort of dropped-in question. And so all of those kinds of things, if you can kind of abstract those, is what you end up seeing. Sometimes then it all just works, you know, and if those are the only errors and everything else is with half of an LSB, you don't usually notice the problem, which is great. On the other hand, you can see all sorts of interesting problems. One of the first ones that you would hope for a DAC or an ADC, and often can be true, is saying I want it to be monotonic, which means every single level at least increases as I increase code. Or with every increase in code is an increase in voltage, whether it's a DAC or an EDC. Here's the problem. It doesn't have to do that. You can find all sorts of cases where it would happen. And you could have a case where, such as in this case, where as I go from one code here, from 001 to 100, which is a classic case right at that edge, it actually went down in terms of its output voltage. And you think to yourself, that's not helpful. That actually means that there's a real interesting problem between these two. This is a very common problem to happen. You could see this again in the same curve here as it goes up. What you realize is that, yep, this should have been nice and monotonic, but looky here, this drops. Again, notice it's right at the sort of most significant bit boundary edge. Often happens here because the issue at the most significant bit is that I've got to make sure my components for the most significant bit have the matching to the LSB. And so that's the thing that usually catches you in terms of matching of devices. So one would not be surprised to see this in a lot of different characteristics. And so you would want it to be monotonic. You don't always get monotonicity. A classic DAC where you pretty much can guarantee monotonicity is if you do a ramp ADC. Because after all, you're building a ramp that is going monotonic. But in other topologies, you cannot guarantee monotonicity. The other aspect would be in a flash ADC with a set of, say, resistor-generated codes. Those are cases where it would be monotonic. You don't always get that. And so one of the things that you'll see if you're looking at ADCs, you're like, well, I can have some changes, and yeah, maybe it's a little bit off, and so obviously now there's both some INL and DNL errors, and this continues to change, and maybe there's effectively a gain error up to the most significant bit, and then all of a sudden I get a very large jump that kind of self-corrects, and then it kind of works its way back. And so I can see a DNL error that's bigger than an LSB. The INL error then in this case is significantly sizable as well. I can also get cases because of the non-monotonicity of an INL error being, I can get INL errors that are like 2, because, it's supposed to be here and actually here, so you're like, that's a problem. Non-monotonicity typically, is something that you can actually make sure you're okay if you assume that the DNL number is bounded. If it means that at least my DNL is always, never worse than sort of 1 LSB, then I'm usually okay. And so this is one of the reasons that we'll have to look at the DNL question, because it'll give us a question of the monotonicity. And so I can then also, again, look at this and I can see multiple issues. Here's a 1.5 LSB INL, and you get a sense of what that looks like physically. But usually if I get an error like that, I'm going to have something else later. I'm going to have some other issues later on. And so it's important to kind of take a look at what these kind of curves look like. Now, real DACs are typically, 6, 10, 12 bits. So you may not notice these things initially until you look deep in the curves. And then you go, wait, this is where I'm getting some interesting issues. And maybe that interesting issue is like right at the most significant bit, which might be your 0. Right, because you'd be 0 and you go plus or minus around that point, and you're like, well, I wonder why 0 is not well defined. And these are things that you might get, or there's some error in it. So be very aware what these characteristics can mean, and there's a lot of subtlety in all of these pieces when you look at them carefully.